All right, we're about to pull back the curtain on a really strange mathematical mystery that's happening inside your computer, probably right now. It's this weird little quirk that can make even the most basic math go, well, a little bit wrong.
So let's start with something that looks super simple. 1/10 plus 1/10 plus 1/10 equals 3/10. I mean, that seems completely 100% true, doesn't it? It's the kind of math you wouldn't even think twice about.
But here's the crazy part. If you ask a computer to check if that statement is true, in a lot of programming languages like Python, it's going to come back and say, nope, false. Which is just bizarre, right? We're not talking about some high-level calculus here. This is elementary school stuff.
So it really makes you wonder, how on earth can a machine that's built for perfect logical calculations get a simple sum like this wrong? Is your computer just broken? Is it a bug in the system? Well, the answer is no, and the reason why is actually pretty fascinating.
To get to the bottom of what the computer is doing, we actually have to take a step back and look at a problem that you're probably already familiar with. Yep, we're going to have to rewind all the way back to grade school math for a minute. Do you remember the fraction 1/3? When you try to write it out as a decimal, you get 0.3333, and those threes just go on forever. No matter how many threes you write down, you can never, ever get the perfect, exact value of 1/3. You're always just getting a little bit closer. And that little gap, the difference between the perfect idea of 1/3 and the messy decimal we actually have to write, well, that has a name. It's called a representation error. It's just the reality of trying to fit a never-ending number into a finite space. And it turns out, computers have this exact same problem, just with totally different numbers. Okay, so here is the absolute key to the whole puzzle. What we're seeing isn't a math error. The computer isn't bad at adding. It's a translation error. It's trying to convert our numbers into its own language, and, well, something's getting lost in translation. Let's put our world and the computer's world side by side. We think in what's called base 10, using 10 digits, 0 through 9. And for us, a fraction like 1/3 is messy. It repeats forever. Now, computers work in base 2, or binary. They only use 2 digits, 0 and 1. And in their system, our nice, clean, simple number, 0.1, is their version of the messy infinite one.
So when you type in a nice, clean 0.1, the computer sees this crazy, endless string of ones and zeros that just repeats on and on and on. And just like we have to eventually stop writing 3s for 1/3, the computer has to chop this binary number off somewhere.
Exactly, because a computer doesn't have infinite storage space. It has to make a cut. As the source material says so perfectly, stop at any finite number of bits and you get an approximation. It stores a number that is incredibly, incredibly close to 0.1, but it's not exactly 0.1. Now, this isn't just random guesswork. There are rules for this. There's a global standard called IEEE 754 that basically tells every computer how to handle these approximations. For most numbers, this rulebook gives the computer 53 binary digits, or bits, to work with. And for our number, 0.1, the closest it can get within that 53-bit limit is that, giant fraction you see there. So just think about it. You sit down, you type 0.1. You see it on your screen. Looks perfect. But what the computer really stores, deep down, is this number. Look way, way at the end. See that tiny little tail of digits? That 555? That's it. That's the phantom number. That is the representation error. And most of the time, our software kindly hides this tiny imprecision from us. But when you add 3 of these slightly too large numbers together, the final sum just doesn't quite match the computer's slightly too large version of 0.3. So, if this is just how computers work, what do you do if you actually need perfect accuracy? I mean, if you're building banking software, close enough isn't going to cut it, right? Well, thankfully, programmers have special tools just for this job.
In languages like Python, there's a whole toolkit for this. If you're adding up a huge list of these numbers and you're worried about those little errors building up, you can use something called math.fsum. For anything involving money, you absolutely use the decimal module. It forces the computer to do math in base 10, just like us, which dodges the whole binary translation problem completely. And if you need pure mathematical perfection, you can use the fractions module to work with the number as, well, the fraction 1/10. No approximation needed.
So what it really all boils down to is a trade-off. For most things, like calculating graphics in a video game or analyzing scientific data, the default numbers, called floats, are super fast and efficient, and that tiny little error doesn't matter at all. But when every single digit is critical, like in financial systems, you switch to these more precise, albeit slightly slower, tools.
So let's wrap this up. After diving into all this weirdness with phantom numbers, what's the big idea we should walk away with?
The most important thing to remember is that this isn't a bug. It's a feature. It's a deliberate design choice made for speed and efficiency. For 99% of what we do, that microscopic error is completely irrelevant, and our programming languages are smart enough to hide the messy details from us. But knowing that it exists is incredibly powerful. It explains those strange, once-in-a-while results, and it tells you exactly when you need to reach for a more precise tool for the job.
And that leaves us with a final thought to chew on. We've seen how a super simple sum can be just a tiny bit off. But where else might these tiny, phantom numbers, accumulating over time, have a huge impact? Think about it. A GPS satellite navigating for years, the interest calculation on a 30-year mortgage, or a long-term climate model. Suddenly knowing about these phantom numbers isn't just a fun fact. It's absolutely essential for building a reliable world.